Let's get going. So today we're going to finish up our discussion of magnetism. And so we're going to focus, at least initially, on the idea of Amperes' law. And so we're going to find that Amperes' law has a similar purpose in magnetism as Gauss's law did in electricity. And so with that, we're going to end up doing some integrations here. But again, there are special integrations where we'll only do sort of the easiest possible cases in most of the situations. And so we're going to start with this definition of what's called a line integral. And I do talk about this in the video a little bit. The book talks about this too, so that hopefully there's some places to get some follow-up, because more than likely you haven't seen a line integral before. But basically, here's just some line going from I to F. And you can use, one way if you wanted to sort of figure out the total length of that line would be to cut the line into little segments of length delta S, right? And basically add them all up. And so here, it's sort of a pretty good job. But of course, since this is a curvy line, these delta S's aren't exactly the same. And so this works better if the delta S's come to a size of 0. And that's where the sum here turns into an integral. So you can integrate I to F over ds. And realistically, this is the only integral we'll end up doing. Okay, so in some sort of a situation where we have from I to F ds, and of course, in that case there, right, if we're actually doing this, if I'm going I to F, integral of ds, what that does is just gives me the length of that line that we're talking about. Okay, and so this is a way to sort of integrate to do that. Now, in reality, to do it like on this line, it's not easy. You can't just sort of do a nice integral to do that. But conceptually, what we're trying to find here is actually measuring the length. And so this is the sort of key. So if you kind of buy this idea, you're set. So just like with Gauss's law, there's this scary integral-looking thing, but we're really just kind of looking at what it is conceptually and using what it is conceptually. So anybody got a question? So, a big question yesterday was, what is this ds supposed to be? And so the ds is just you're integrating over some line, so we can't necessarily pick like dx or dy or something, but it's basically you're integrating over this line, trying to find the length. And for us, we're always, if we end up doing this integral, we'll end up with a situation where we have a simple case like this, where I'm just basically trying to find the total length of the line. And so it's more of a conceptual thing that we're trying to get at. So we'll go through and do some examples, but hopefully that part there makes sense. And so for us, we're going to be focusing in on this particular line integral. And so just like with Gauss's law, there'll be a little circle here. And so we're going to be looking at b dot ds. Okay, where again, ds is just some distance. And as it's a dot product, okay, for us what will happen is this will, more often than not, 90% of the time when you look at problems like this, you'll break it down like this right here. So say, okay, well, the b dot ds is the magnitude of the magnetic field, the magnitude of that ds vector times cosine theta. And again, what we'll be doing is there'll be some path here, and we'll have some point, and we'll sort of rotate around in some direction, which will be important. We'll rotate around, and then as you go around that path, okay, the B field will have some relationship to ds. And so if I just pick some point, like say right here, ds is just the vector that's tangent to that particular point that we're talking about. Okay, so if you look at some point on there, the ds is again just a point that's tangent. If I was picking it over here, my ds would be kind of going that way. And so at any point when you do that, you can look at what the magnetic field is. And so this angle, theta, is the angle between the magnetic field and this distance vector that we just call ds. Sometimes you'll see this as dl, different things depending on who you're looking at. And so again, for us, just like with Gauss's law, we're going to be looking at cases where there's symmetry. And so for us, the interesting cases will be cases where theta is either 0 or 90. And in both these cases, we'll be looking at only where the B field along our path is constant. Otherwise, this integral isn't very much fun, and it's not going to be useful to us. And so this is a case here where the magnetic field and the ds are parallel. Okay, that's what angle of 0 means. An angle of 90 means that those two things are perpendicular to each other. And so if we look at those two cases, and again, take this integral here. So here we've got this integral, so the magnitude of b, magnitude of ds, cosine of 0. So cosine of 0 is just 1. And so what we end up can do is pull out the magnitude of our magnetic field. And then here we get that situation we were just talking about where it's just the integral over ds because that magnetic field is constant. And so it's like the magnitude of the magnetic field times the length of whatever path we pick. Okay, and so we'll go through and we'll figure out sort of the paths to pick. But so in reality, we'll only do those sort of two cases. And in that case, it's just b times L. In the other case, it's actually going to be easier. So when theta is 90 degrees, right, then this whole thing just becomes 0. And so cosine of 90 is 0, so the whole thing is just 0. So there really will only be 2 times we'll be doing this integral, and it'll work out to be either b times the length of whatever we're talking about, and in the other case, it'll be 0. And again, it's similar to what we did with Gauss's law, if you remember. We only really looked at situations where the electric field was constant over our surface, and so it came out to be, the actual integral often, again, like 90% of the time, and all the problems in the book are situations where it's a nice, easy sort of way to set up the integral. Questions on this? Anybody? Because again, I think just half of it is just kind of understanding in words. I mean, it looks really scary mathematically, but it's much more just about kind of words that we're using here and concepts, I think. And so here's just a little picture kind of summarizing that. So for the actual situation that we'll see, again, these two situations primarily, the case where when you're going along your path, the magnetic field is always perpendicular, or the case where it's always in the same direction. And so in this case, it's just literally b times the length. Again, it's a nice constant magnetic field. In this case, it's 0. So almost all of our cases will be able to boil down to those two situations. And so what this thing does is, in a sense, it kind of tells you how parallel the magnetic field is to your path. All right, in that first case, it's completely anti-parallel, so it's 0. And in the second case, it's completely parallel. And so it gives you sort of a sense in that case. So let's look at our example from last night. So this was a big question. So let's talk with our neighbors and see what you guys think. So here we're trying to do, and one thing is, I guess here we shouldn't have that circle because a circle means you have a completed path. But anyway, so you're looking for b dot ds going from I to F here. What do you guys think when you do that? Okay, so I was pretty happy with last night. I think most people kind of got the idea here on this one. So again, this is the situation as we were just describing. So there's two cases. This is the case where the magnetic field is parallel with your path the whole way. All right, and so this is the kind of case where if you're being technical, you take this integral and say, okay, it's b times ds times cosine theta. That's a 0. So I get rid of that. My b field is a nice constant. So I pull that out, and so this works out to be b times L. And even in the cases where the book will make this harder, they'll just do something where like the magnetic field increases linearly or something. So you're sort of integrating over like an x or something. So not even that much trickier. But for us, we'll keep it to stuff like this. And so it's literally just the B field times your length when you do this. And so in our case here, then, the magnetic field is 0.01 Tesla. And then my length here, so this makes a little triangle, like so. And so so both of these sides are 0.05 meters, because they're 50 centimeters. And so this side here, I would call radical of 2 times 0.50 meters, which is like something 0.707 meters. So that's the actual length there. So that might be the, just doing a little bit of geometry. And so I put this in over here. And when I calculate that out, I get this answer up here of basically 7.07 times 10 to the negative 2. Now the units would just be Tesla times meters, right? It's magnetic field times length. So that would be the units you'd get out of this here. And again, that's an example of sort of the hard way of doing this. The easy way would, if it was all parallel, would have been 0. Okay, so questions on that? I think a lot of people got it last night, but still some confusion on this here. But that's what we mean by this line integral. And again, for us, we're only going to look at situations where the B field is constant and it's either parallel or anti-parallel in our situation here. And that's really the cases that are most interesting and most useful as well. Okay. So let's do the other one from last night. So this one's kind of a more conceptual picture of this idea of what Ampere's law is. And so let's see what we get. So for the path shown, B dot ds is equal to what? So let's discuss this and see what you think. Okay, so let's look at this here. So here's the responses. So the good news is I think I agree with the majority, and I think the people who picked A, we can talk about that and hopefully clear that up. So let's look at this here. So we're going to find that our Ampere's law, like Gauss's law, so it takes this integral thing. So here it's a different kind of integral, but we do this integral B dot ds. We've been talking about this line integral, and that's going to equal u naught or mu naught, our constant, and then I, and what we would sort of say is that the sort of the total current that's enclosed by that loop. Okay, they're sort of encircled by that loop. So we'll say maybe total or something like that. Okay, and so here the key point I think is that we can't say that I1 is like the magnitude of I1 is equal to I2, or at least we didn't say that yet. Okay, so we just said there's two different currents. And so, as far as we know, this current is, like 3 amps, and this current could be 4 amps or something. So there's nothing in this problem that says that the two currents are the same. And so that's why I would not pick A as the answer. Would in fact pick B. Okay, and so this is an example. If you remember in Gauss's law, when we started out doing it, we sort of had some simpler pictures just to kind of understand fundamentally what's happening. And what's happening here is again, you have this situation where on the left side, there's this really nasty integral thing that everybody wants to avoid. And on the right-hand side is this thing that can save you time. And so in these kind of situations, it's almost always easier to think about the right-hand side. All right, and so this says, this law says that B dot ds, that integral, that line integral, is always equal to mu naught times the total currents that you have piercing through your surface. And a way to think about that, just to be a little bit clearer, is imagine that there was like a soap film covering up this this circle. So it's like literally a circle. So it's like a little ring. So imagine if you put the ring, into some, soap or something and pulled it out. And so you have this film of soap. And so literally what we're looking for is we're looking for all the currents that are piercing through that film of soap. So in this case here, there's two currents, I1 and I2. And really the only tricky part, the only ambiguous part is just which one's positive and which one's negative. And the way you use that would be the right-hand rule. So someone has to tell you which way you're doing that integral in that situation. If you look here, I just kind of covered it up with all my soap film stuff. But if you look here, okay, the path is going this direction here. And so if you sort of take your fingers along with the direction of the path, my thumb will be pointing upwards. And so the definition of this path would make any currents going this way positive currents. And so that's why we have I1, minus I2 and not the other situation. So there is some ambiguity as far as the sign, but you can, if you know the direction of the path. So if someone had decided to do the path the other way, we would have gotten the other answer, okay? And you can imagine even just going back to this definition we had here, this guy here. And so in this case, when I go from, I to F this way, I get B times L. But you can imagine if I went from F to I, I'm going the opposite way. And so the angle between my ds and my B would be like 180. So I'd incur a negative sign and get negative B times L. Okay, and so going the other way just sort of flips that sign is what it essentially does. And so for these kind of problems, you need to know the definition of which way we're going around that circle in order to answer them. Okay, so I would agree with the majority that it would be B. And so the reason it can't be is that, so it could be that, right? We didn't name these, but it's possible we could have made them the same current. But in this case, we did not say that. So you can't sort of assume that. So I can see where those people are coming from. Questions on that one there? So this is not true. Okay. So this is our definition of Ampere's law. We just used it, which is kind of cool that we can go through and use it. So just like with Gauss's law, it's a way that we can solve for the magnetic field in different situations that can be much quicker than doing it other ways. All right, so we talked briefly about the Biot-Savart law last time. That's the really nasty way to do these things. You can do this generally much quicker and much more pleasantly using Ampere's law. But it is, again, tough to sort of get your head around. Okay, so let's go ahead and look at this question here. This is kind of sort of a conceptual version of what this Ampere's law is even telling us. And so here, I just put, 4 compasses. I arranged 4 compasses, magnetic compasses, and set them up. And they're pointing, so the colored in section would be the north side. And so they're sort of, they go this way here. And so by looking at what these compasses are doing, you can tell stuff about the current that's going sort of into the page or out of the page there. Okay, so talk with your neighbors and see if you can figure out which way the current's going. Okay, and so I agree with the majority. So it looks like the majority of us are saying B. So I agree with that. And so what are we saying here? Well, if we were to draw a picture, and so maybe this is, I could make a loop through here. Okay, sorry, not a very good loop. But if I was doing my loop and kind of going around this way, you can see that the magnetic field is going to be trending in a circle around there. So we know from previous sort of cases of doing this so if I put my finger along with the magnetic field this way, one of our right-hand rules, the current would be pointing this way. So we can argue that the current should be going out of the screen. And that's what the whole idea of this Ampere's law is. With Gauss's law, we could sort of, make a surface around some charge. And if you looked at the electric field on that surface, we could kind of tell what kind of charge was in there. If the electric field was always pointing out, that meant there was like a positive charge in there. If it was always pointing in, it was a negative. It was some combination of the two. We could determine what it was. And so this is the same idea. If I sort of make a loop, okay, and look at the magnetic field on that loop, I can tell a lot about the current that's piercing through, again, that soap film sort of connecting the loop. And that's what you did here. You did it using stuff from before, but it's the same concept of what's in Ampere's law, right? We can sort of know a lot about the current piercing through that soap film if we know about the B field on that loop. And so here's the kind of classic situation that you would study this in. And so just like we just did, you can look at it in terms of this, this wire coming out. Okay, sorry about that. And so let's look at this. So here's kind of the classic case of what we would use Ampere's law for. And so I can set this up here and say, okay, so here's my new equation, Ampere's law. So B dot ds equals my U naught times my I. And so this side here, all right, so we're looking at this caused by a wire loop. And so again, we can only look at situations where we have a nice symmetry. So we have this, current going into the page in this case here. And so I know my magnetic field in this case for the circle I picked has to be constant, and it has to be, parallel to that circle, okay, because what we know about magnetic fields. And so that's our symmetry. So since we know that it has to be constant, and it's constant because it's the same distance from the wire, and we know how it has to curl, then we can look at this picture here and look at our B dot ds and argue to ourselves, okay, well, B dot ds in this case will just be B times L, our length, okay, the length of the path that we're taking. So as usual, in this case where the angle is 0 and it's constant, it's just B times L. And so here I called the radius to be D, and so my actual path length would be 2 pi times D. So it's the circumference of this circle. And then what I do is I equal that to mu naught times I, and then what I'm solving for then, you can sort of, actually this would be as a function of D, and so it's the magnitude of the magnetic field as a function of D is mu naught I over 2 pi D. So in this example, they chose to use D as the radius, but we used R before, but hopefully you remember this equation from last week. And so now here we can sort of go through from this Ampere's law and actually calculate this magnetic field. Again, just like with Gauss's law, it seems a little bit like you're doing magic at first. And so we want to go through and kind of try to understand this a little bit better. But any questions on that there? So we can draw a picture sort of like so. So here's maybe some current going into the page, and I can get sort of two loops. And so we'll call this one to be R1, and then this one over here to be R2. And so they'll have different magnetic fields. So on this loop, you would call the magnetic field B1, and on this one, you'd call it B2. And so what happens is if, again, we calculate this B dot ds business that we're talking about, so again, it becomes the B times the L. And so in that first case, I would have B1 times length 1. And my length 1 would be 2 pi R1. And in the second case, I would have B2 2 pi R2. And so we know that our magnetic field in this case would be like U naught I times 2 pi, and it would be R1 in that first case. And so you see that the 2 pi R1s cancel, and you get the same value, U naught I, no matter what you do. And so the same thing over here, if I was to do this over here. Okay, so if you actually plug in, remember that our value for the magnetic field as a function of R that we've been talking about for a couple of days is just this one right here. And so again, no matter which path you take, you get mu naught times I. Okay, so if I take the inner path or the outer path, and so literally what's happening is because this thing goes linear as the distance r, which also the circumference goes as, those two effects cancel. And again, that's the same thing we had with, or a similar thing we had with Gauss's law, just that that was a surface. And so the electric field decreased as 1 over r squared the further out you went, but the surface area was 1 over r squared, so those two effects canceled. And so that's one of the reasons, or that's how you can think about, one way you can think about why the integral over the surface area in Gauss's law was always equal to the charge enclosed. It's the same sort of idea here. And then if you want to think about, well, what if I make a loop, you know, that doesn't include the wire there. So let's make a loop here. Let's just sort of make our own special kind of Amperian loop like this here. Okay, so suppose I start here and I go around this way in a closed loop and come back over here. All right, and so I have sort of 4 legs to this thing. You can sort of think this is the first leg, the second leg, the third leg, and the fourth leg. And so if I was to do, again, this B dot ds in this case, so I'd have contributions from the 4 legs. And what I would have is from leg 1, I'd have something like B1 times some distance, I'll call it L1. For that number 2, since I'm sort of moving radially, that's a case where the magnetic field is perpendicular, so that'd be plus 0. For this 3, and actually I should be careful, so this would be a negative B1 L1. And then for this length 3, I'd be back at that B2 times L2 and then plus 0. And so what will totally work out here is that these two things are going to add up to be 0. And so there's a negative contribution and a positive contribution. And again, since our current is going into the page, our magnetic field is going to be going in a clockwise direction from your guys' viewpoint. And so for that path 1, I'm going against the clockwise, so I get a negative B times L1. And for that path 3, I'm going with the clockwise B times L3. And it totally works, again, because of this idea that, you know, that the B field gets weaker by a linear factor of r as you get further away, but that arc length difference increases. And so these two things will exactly cancel out. So this is an explanation of sort of why the currents outside, okay, don't contribute to this. They'll always work to be adding up to 0. So it's only the currents that are inside your loop that you pick that will have an effect here. Questions on that? Okay, so before we move on with that, I wanted to look at here. So like I said, now that we're getting into magnetism, the demos we have are a lot more fun. And so this one here is, again, one that's dangerous, so please don't touch it. So what we have here is we have 2, that's not, yeah, don't touch it. We have 2 wires here. So this basically, this thing is set up. We have 2 sort of aluminum or copper tubes here that we're going to run current through. And so what we're going to see here is this effect that we've been talking about, that, you know, current carrying wires can repel or attract. Okay, and I think I have it set up here on the situation where it's going to repel. So I'm going to turn this thing on, and it's going to send current through these things, and it should attract. And again, a good rule of thumb is always only touch stuff with one hand. Okay, so let's see if this works. Yeah, so you can see that the current going this direction goes that way. And so this is repelling. Whoop. And then what I can do is I can go over here and switch it so that they attract each other too, if we want to do it that way. And I think as we go on, you'll see that we'll get sort of, so we put it on the side where it should be attractive now. And so in this case, they should stick to each other. Yeah, okay, well, that's pretty great. Yeah. All right, so just kind of show that this does work, right? It's just that, in situations for us in our everyday lives, the current we have in most things is pretty small. And so you got to get sort of extreme cases like this to see these actual effects in most cases. Okay, so let's look here. This is kind of a technical one. Let's look at this one here. How does the value of the line integral of the electrostatic field along a closed path encircling a charge distribution. Compare with the value of the line integral of the magnetic field along a closed path, so the one we've just been looking at. So basically we're doing the line integral of the magnetic field, but what happened if we did the line integral of the electric field? So talk that over with your neighbors and see what you think. Okay, so let's talk about this one. So if we look at where we are right now with this one, so there's some A and C seem to be the big, and so I would go with C in this case. So first of all, we just talked about how, this B dot ds for the magnetic field is not zero. It equals U naught times I in general. And so that's the first thing that we can kind of think about that way. And so let's look at what this would be for the electric field. And for the electric field, if you remember, we've talked about this a little bit. Okay, so here, if you remember, we sort of discussed stuff like this when we talked about the electric field, but it's been a while. And so our work, the integral for work in general, is this integral of the force over distance, right? And with the electric field, since the force equaled Q times the electric field, we could write the integral here to get E dot dl. And that's really, that thing there is a line integral over the electric field. Okay, that was our definition of the electric potential, was sort of the difference between A and B, E dot dl. And so this thing here had a very specific meaning to us in electricity as well. And if you recall, what we could do with that then is situations like this. And so this is actually something we used on a test, which was the fact that the path between, like, say, A and B was independent. Okay, so the work done by electric field, no matter what path we took, you get the same amount of work. And the way we kind of reasoned through that is here, if I'm sort of taking this path, I only count the parts where I'm working either against or with the electric field. So if we sort of break this path into like sort of this little jigsaw thing, it's only the paths where I'm going up that have an effect. And so the total work done is the same whether you go from any path you take. And that was our picture we had with electricity. And so what happens in electricity then is kind of a different situation. And so I apologize, this didn't really, this integral sign should be a nice integral with a circle through it. I'm not sure where this weird rectangle came from. But in electrostatics, E dot dl is equal to 0. And that's just the idea that, and we use this to solve circuits, if you remember, is that if I just go around any path, the change in my potential differences always came out to be 0. And so it's the same sort of thing to say that, that means that sort of the work as I go around any closed path is 0. So this E dot dl, this line integral for electricity, will be 0 for the electric case, and it will be, again, not 0 for the magnetic case. So there's a difference there when you get to these integrals here. And you can kind of think about it like in this picture here, here I'm kind of going parallel to the E field lines, so I'm not really doing too much work here. But then here I'm going against the electric field. So if I was a positive charge it would be doing negative work. Here I'm kind of not doing any work, and then here I'm going with the electric field, so it's doing positive work. And so those two contributions would cancel out. Okay, so just kind of, it's nice to just compare with stuff that we've done before and talked about. Okay, so let's look at some other cases. So here we have the value of B dot ds in this particular situation is 3.77 times 10 negative 6 Tesla meters. I want you guys to find out what is I3 in this case here. So talk it over with your neighbors and see what you think, and we'll talk about this in a second. Okay, so let's look at this. Probably didn't have enough time to figure all this out, but hopefully you got enough to start thinking about it. So we'll use our B dot ds is equal to mu naught. And then, so this is, again, sort of the total current. And so over here, I can take this, which should be this number here. Okay, so I can take that and divide by that mu naught. And so if I divide both sides by mu naught, okay, here I get my I total. If I take this number, 3.77, 10 negative 6, and divide by my mu naught, when I did that, I got a value of 3 amps. So that's why this number is so funky, is I was trying to get it to equal out sort of a nice number. And so then 3 amps, we do something like this. And so if you look at the sign from the path we took, if I do my fingers in the direction of the path, okay, in that loop, my thumb will point in. So if my thumb points in, that's the direction we have for positive. Okay, so pointing in would be positive. And so if I sort of draw that out here, then we'd have a positive 2 amps, a negative 6 amps, and then plus the I3 from over here that I'm trying to find out. And so this will end up being negative 4 amps plus I3 equals 3 amps. And so if I end up solving for my I3, I get something like 7 amps is what I come out to be. Okay? So again, this is kind of just getting us used to how this idea of Ampere's law works. So one important thing was the sort of sign direction. So you need to know sort of the direction along that path. And so again, you can relate the currents to this line integral B dot ds here. Questions on this, anybody? Yes, okay. Okay. And so finally, just like with Gauss's law, sort of the idea, one of the ideas for this is that we can use this to solve for the magnetic field in cases where there's nice symmetry. And so we're going to look at this case of the solenoid. So again, we talked about solenoids a little bit. It's still kind of new, but we sort of introduced it. And so here I'm going to kind of make some arguments for how the magnetic field should look around the solenoid. So we talked about the magnetic field from a single loop. So the magnetic field from a single loop, you can map it out kind of like this here. Okay, so the magnetic field through the loop would point this way. If you do your right hand rule, your fingers go in at the bottom, out at the top, your thumb points that way. So you can get the sort of, that's what the way that works here. And this would be the magnetic field sort of coming out here. So if you remember, this will look like the magnetic field from a bar magnet. We sort of talked about that. But you can kind of look at 2 different points here. So this one here, at this point, it's again pointing in a general way this way, but it's going to be pointing upwards here. This one's going to be pointing kind of downwards. And then over here, okay, you can see that this one's going to be pointing that way there. Okay, and again, this is just sort of the general trend if you were to sort of treat these as two different wires. And then if we start to assemble 3 of these in a row, like we would for a solenoid, okay, we find that basically they're all going to have magnetic fields pointing that way in the middle. Okay, and so that's what we found when we talked about the solenoid. So there's a big, strong magnetic field that way. And you can look at a point here. So this point is going to have contributions from all 3 of these guys. And so basically, this one here is going to be contributing this piece, which kind of looks like that there. This one here will be contributing that piece, which looks like that. And this one here will be contributing that piece over there, which looks like that. But what tends to happen is that these things, you can kind of make an argument that they're going to cancel out on the outside of the solenoid. And then again, they're sort of adding up to make a really strong constant field on the inside of the solenoid. And so that is, again, what happens, and that was our picture we kind of described last time when we sort of introduced the solenoid. So we got this inside, a nice constant magnetic field, and outside it's going to be weaker, and again, close to 0. And so basically, as you get sort of a more perfect solenoid, an infinite sheet of a solenoid, you get those 2 effects. So it's similar to how we have, like, and for a capacitor, you know, you never have a perfect capacitor, but it's our closest thing we have to sort of a perfect, nice, constant electric field. And so then what we can do is try to use this Ampere's law to calculate some things. And so let's look here. So to actually calculate the magnetic field of the solenoid, I sort of use those 2 assumptions we just got. So I'm assuming that the magnetic field is constant in the middle, and it points in the direction agreeing with our right-hand rule. So I'm going to make my special loop for Ampere's law this rectangle right here, okay? And so the first thing I want to do, and so this rectangle has a height h and a length L, I want to calculate B dot ds for my loop here. Okay, and you'll have to split it up into 4 pieces and calculate what the 4 different pieces are. But again, we're assuming the magnetic field is constant and looks like this inside, and we're going to assume that it's 0 outside of the solenoid. So try to calculate just the B dot ds part with your neighbors, and we'll talk about this in a second. Okay, so let's look at this. Hopefully you've had time to kind of think about it a little bit. But let's see if we can look at this. So we got, again, 4 paths. So here's my path down here. So my path down here, the magnetic field is really nicely parallel with my path. Okay? And so for that piece there, if I go through there, it's the case where our angle is 0. And so I'd get something like, for that contribution, I'd get the magnetic field B, so we're calling that B down there, times the length L, which is the length of my piece here. Now for the part 2, the magnetic field, actually, let's be careful. Outside here, it's 0. Inside here, it's there, but it's 90 degrees. And so for my part 2, I'd have a contribution of 0. So for that lower part, the B field is 90 degrees, so there's no B, B dot ds. And then for that upper part, there's just no B field at all, and so it'd be 0. For the path 3, it's the same sort of thing. For path 3, the B field is 0. So again, we're making the assumption the B field is 0 out here, which is pretty close to real life. And then again, coming down here, I'd have the same kind of situation. And so what we'll end up having is sort of 3 contributions. This is the contribution from 1, from 2, from 3, and 4. So 3 contributions. However, those contributions are almost all 0. And so I'd end up with this piece here, B dot dl. Or, I'm sorry, B times L, or L times B, whatever you want to call it. Okay? Questions on that, anybody? Okay, so let's go ahead and pick this up next time, and we'll start this on. We'll see you guys.